we have section 6.5, L'Hopital's rule and indeterminate forms. So we're back to limits again. So we have two indeterminate forms. We have 0 over 0 and infinity over infinity. And so if we evaluate a limit using direct substitution and get either one of those, we have to try something else. So now we have some other thing that we could try. Before we had to maybe factor, divide out the bad guy. Maybe we had to do some trig manipulation, some rationalization, multiplying by the conjugate, but this we're going to learn another time. All right, so for these, make a guess by what you think the limit will be, then check by evaluating the expression using your calculator. So this is something you should be able to do. Type the function maybe into y1 and then evaluate it. So you should get 3.498, 3.045, and 3.004. So what does it look like it's getting close to? And to me, looks like 3. Okay, the next one, if you plug this in, and we're going the limit as x approaches 1 from the right. So this ends up being 0.492, 0.499, and then this one's 0.4999, which basically is 1/2. And then we have this one here. That looks familiar, or does it? All right, we're in limit as x approaches infinity, so we're going to make the x's bigger and bigger. So this goes 7.244. And then we go x is 1,000, 7.374. So it didn't grow very much in 900, and then we go to 9,000 more to x approaches 10,000, and we get 7.387. So it is approaching something, but maybe we're not really sure. If any of you know what the limit as x approaches infinity of 1 plus 1 over x to the x, if you know what that is, you'll know this, but maybe not. So it's fine. We're going to have to just investigate a little bit. All right, so we're going to review some of those techniques I mentioned earlier. If we try direct substitution, so if we put -1, so we get 2 minus 2, 0 over 0, which is good. We want that because we can do something else. So we could factor x plus 1, x minus 1, cancel that out. There's a hole there, but we don't care when it comes to limits, so we just plug it in. So 2 times -2 would be -4. This one, limit as x approaches infinity, we would get infinity over infinity, which is good because we can do something else. We can evaluate the growth rates here. So this one would be 3/2. And then this one, if we plug in 7, we get 0 over 0, which is good because we know we have to do something else. And the something else in this case, we could do multiply by the conjugate, because then in the numerator, we would get x plus 2 minus 9. And in the denominator, we get this. And in the top, we get x minus 7. The bottom's x minus 7. So we have 1 over the square root of x plus 2 plus 3. Now we evaluate it. So we get 1 over 6. So this is what we did before. We had a couple different methods, factoring, using growth rates, conjugate. Well, we have something else here. Another method developed by the Swiss mathematician Johann Bernoulli. And we call it L'Hopital's rule, not because he discovered it, but he published it first. Okay, so L'Hopital's rule combines limits and derivatives. If you use direct substitution and you get some indeterminate form, 0 over 0 or infinity over infinity, then you can take the derivative of the top, the derivative of the bottom, and then evaluate it. All right, so let's look at these. These are the ones from, is it? I think this is the one, yep, this is the one from the beginning of the day. So if we plug in 0, We get 1 minus 1 over 0. So 0 over 0, which is good. So now what we do, we take the limit as x approaches infinity, take the derivative. 3e to the 3x over 1. Now plug in 0, and we get 3, which is what it looked like we were approaching before. Kind of cool. We could use rationalization conjugation. We plug it in, we get 0 over 0. Good, that's nice, okay? Or we could do this new rule. So if we take the derivative of 1 plus x to the 1/2, we get 1/2, 1 plus x to the negative 1/2 over 1. Okay, so then I guess I would rewrite it just to make it look a little better. 1 over 2 square root of 1 plus x. Plug in 0 now, and we get 1 over 2. Pretty neat. So now, trig, let's see. Let's try plugging in pi over 2. Well, tangent of pi over 2, that's sine 1 over 0, that's undefined. So this is some sort of infinity over infinity, which is fine. So then we have to think, all right, let's try L'Hopital. It seems to work every time, right? All right, so the derivative of secant is secant x tangent x. And then the derivative of tangent is secant squared x. So if we plug in pi over 2, we get infinity over infinity. Okay. Well, that doesn't help, does it? Well, we could reduce, right? Maybe that'll work. Nope, it's still infinity over infinity. Well, let's just try it again, right? Limit as x approaches pi over 2. Derivative of that is secant squared x. Derivative of secant is secant x tangent x. We could cancel one of those out. Guess what? We get infinity over infinity. So now what? Well, do something else. That's what that means. Sometimes this works, and sometimes it doesn't. Sometimes you end up with an infinite loop here. All right, so now we got to think about it a little bit differently. So going back, oh, I should have kept that. That's okay. All right, so we'll do it one time. Secant x tangent x. We could do it from here. Come on, computer. We could do it from here, but I'll go back to this. And then the derivative of the bottom was secant squared. So we cross that out. So now we have tangent over secant. Well, tangent's sine over cosine. And secant is 1 over cosine. So 1 over cosine is just cosine. So that's the limit as x approaches 1/2 pi of sine of x. And sine of 1/2 pi is 1. All right, last example on this page here. We have infinity over infinity. So do you feel like taking the derivative of ln of x and then square root of x? We can. It works. Or you can use growth rates if you know them. If you know the ln, the natural log of x, grows so slowly. That's one of the slowest growth rates we have. And then square root of x grows a little bit faster. So if the bottom is getting bigger faster than the top, then this derivative, or this limit, is just 0. Okay? Now, sometimes we need to repeat ourselves. Sometimes we need to repeat ourselves. So if we plug in negative infinity, we get infinity over e to the infinity infinity. Well, that's great. So let's try L'Hopital. 2x over negative e to the negative x. All right, so we would get infinity over negative e to the infinity, so negative infinity, so we get another indeterminate form. Let's do it again. Limit as x approaches negative infinity, 2 over e to the negative x. And if you don't like thinking about it like that, we can rearrange this. 2e to the x. plug in negative infinity. So that would be an exponential decrease, which would be 0. All right, and then let's see this one. All right, let's just take the derivative. Let's go for it. Limit as x approaches 0, 1/2, 1 plus x to the negative 1/2 minus 1/2 over 2x. Let's clean that up. So we have, or no, you know what? Leave it, because I'm going to take the derivative again, because I noticed when I plug in 0, I get 0 over 0. Limit as x approaches 0 this time, negative 1/4, 1 plus x to the negative 3/2 over 2. I know I'm not going to get 0 over 0, so let's make this look a little better. We have limit as x approaches 0. That would be negative 1/8. This is in the bottom, and it would be square root of 1 plus x cubed. So plug in 0, so we get negative 1/8. All right, so we'll do one last example here. You have to be careful when you evaluate one-sided limits. Let's see, so we have sine of 0 is 0, x squared is 0, so we get 0 over 0, and that's good. Let's try L'Hopital. Derivative of sine is cosine, derivative of x squared is 2x. Cosine of 0 is 1, and because if we think about cosine, right, it looks like this. And so 2x is 0, so we would get 1 over 0. Now, is that positive or negative infinity then? And since this was positive here, this would be positive infinity. This time, let's look at it from the left. Limit as x approaches. Sine of 0 is 0, over 0 is 0, indeterminate. So we take the derivative, cosine x, 2x. Oh, and so since I wrote positive infinity, let me think about that. We could just put DNE, remember. You don't have to be specific. So we would get cosine of 0 is 1 over 2x. And let's see, just to think about that, 2x, remember, looks like this. So this is a negative value as we approach 0 from the left. So technically, it would be negative infinity, but remember, we can just put DNE. So either of those answers are fine. And I think that's a good place to stop for today.